All right, so let's say we are given a trapezoidal loading as can be seen on the board, and we are asked to do the shear force and bending moment analysis for this kind of loading. It's very simple. First thing first, if you take a look at this diagram, you're going to see that this is actually a combination of two types of loading, the UDL and the UVL. That's simply the uniformly distributed load and the uniformly varying load. Now, how do you find this out? Now, all you need to do is simply section from here or cut out this point. If you cut out this point, you will see that you have been able to split this load into two. So the maximum intensity of this load here is 100 kilonewtons. Here is 200 kilonewtons, which means here is simply what 100 kilonewtons as well. Okay, and of course, I can cancel this now. Here becomes 100 kilonewtons and here remains 100 kilonewtons. So both of them simply gives us 200 kilonewtons. So you can see that this is actually two loads in one. Let's say distance here is simply 5 meters, that's distance apart. So you're having a trapezoidal loading, simply a UDL or a UVL on top a UDL. That's the situation. First thing first, you start with the free body diagram. You have to first of all find the reactions at point A and find the reactions at point B. Okay, so you pull down your beam. At point A, we have a pin support, and for a pin support, we always have two reactions, one vertical and one horizontal. So you simply indicate this RAY, and this is simply RAX. This is point A. At point B, we have a roller support, and for a roller support, we have just one reaction, normal to the surface. So you indicate that just one reaction, RBY. Now, problem now is how do we then convert this UDL and this UVL? Okay, so let's first of all consider the UDL. The UDL load has the highest intensity as 100 kilonewtons, as can be seen on both ends, 100 and 100. That's the uniformly distributed loading. To convert a UDL to a point load, remember, always multiply the load to the length covered. In this case, this UDL is covering the entire length of 5 meters, so it means the point load becomes, please, kilonewtons per meter. Take note, kilonewtons per meter. Okay. Okay, so to convert this point load now, this UDL load to point load, it simply becomes 100 multiplied by total length, which is 100 times 5. So the point load becomes 500 kilonewtons. Then to place this point load on the beam, you place it at the middle of the length covered by the UDL. The UDL length is 5 meters, middle is simply 2.5. That's 5 divided by 2. So it means that the point load of this UDL will act somewhere here, and that's simply 500 kilonewtons. So from point A to this point is simply 2.5 meters. Okay. And from this point to point B is also 2.5 meters. So that's the first thing to do. Convert the UDL load first to a point load, which is this down load. Now, on top of this UDL, we have a uniformly varying load. The highest intensity of this load is also 100 kilonewtons per meter, and then the length covered is also the entire length of the beam, which is 5 meters. So we need to convert this UVL to what? A point load. Remember, the rule to convert a uniformly varying load to a point load is simply what? Take the area of the shape. The area of this shape is triangular, so it simply means that the point load of the uniformly varying load is simply half base. Base is simply what? The length covered by the UVL, which is 5. Half base times height. Height is the maximum load of the UVL. The maximum load of the uniformly varying load here is 100 kilonewtons per meter. So multiply by 100. Okay, so it means that the point load of this uniformly varying load will simply becomes 50 by 5, 250 kilonewtons. Will simply become 250 kilonewtons. So this becomes the point load of the UVL, the point load of the uniformly varying load. Now, after converting this to a point load, next is to place this point load on top of the beam. Now, to place this point load, it is simply you place it at 1/3 from the base, 1/3 of the length from the base of the beam. This is called the base, and this is called the tip of the UVL. This is called the base of the UVL, and this is called the tip of the UVL. So simply at 1/3 of the length from the base of the UDL, or 2/3 of the length from the tip of the UVL. Now, what does that mean? The length of the UVL or length covered by the UVL is simply the entire length of the beam, which is 5 meters. So 1 over 3 of 5 is simply 5. 1 over 3 of 5 is simply 1 over 3 times 5. And that's simply 5 all over 3. And 5 over 3 will simply give us what? 1.7. 5 over 3 is simply 1.7. This is now the distance from the base of the length, or you place it at 2/3 of the length from the tip, and 2/3 simply means 2 all over 3 of the length. The length is 5. This becomes 10 all over 3. 5 times 2 is 10. It becomes 10 over 3. And 10 over 3 is simply 3.3. And of course, if you add 3.3 to 1.7, you will simply get 5, which is the entire length of the beam. So all you do now is, from the tip, you either measure out 3.3 out of 5, or from the base, you measure out 1.7 out of 5. It's as simple as this. So whichever way, they will still land at the same distances. Now let's measure from the tip. 3.3 out of 5 is simply 5 minus 3.3. And 5 minus 3.3 will simply give us 1.7. So let's check now. We already have here 2.5. If we have that to be 2.5, if we move further a bit, what do we add to 2.5 to get 3.3? Because we're moving now from the tip. We're moving from the tip, so we need to measure at 3.3. What do we add to 2.5 to get 3.3? We add 0.8 to get 3.3. So which means this load will be found here, and distance from here to this point is simply 0.8. Meanwhile, distance from here to this point, okay, from A to this point is actually 3.3 meters. So we have here to be 0.8 meters. So this is where the point load of the uniformly varying load acts, and the value of the UVL load is simply 250 kilonewtons. So you have this load, 250 kilonewtons. Okay, you have that load, 250 kilonewtons. So distance from point A to where this UVL load is acting is simply 3.3 meters. That means remaining distance from this point, okay, to the base, which is point B, still remains 1.7 meters. And of course, 1.7 plus 3.3 will still give us 5 meters, which is the entire length of the beam. So it means now that distance from this point, okay, to point B, or from the UVL load now to the base, remains 1.7, as can be seen. So the rule is, you position it at 1.7 from the base, or at 2.3 of the length from the tip. Whichever way, they will still arrive at the same distance apart. So this becomes the free body diagram of this given system. So you simply employ your equilibrium equations to find the reactions at A and reactions at B. Okay, first law, summation of force in the x-axis, or summation of horizontal force, is simply equal to 0. And if we look at this beam, the only force pointing in the x-axis is simply RAX. So that simply means that RAX is simply equal to 0. That's off. Next equilibrium law, summation of vertical force, summation F of y, is equal to 0. We consider vertically upward force to be positive, downward force to be negative. Okay, so forces pointing upward, we have RAY pointing upward, so it's positive. You simply have RAY. You have 500 kilonewtons force acting downward, so it's negative, minus 500. You have 250 kilonewtons force acting downward, so it's negative, minus 250. And finally, you have REY pointing upward, so it's positive, plus REY. And the whole of this is equal to 0. Okay, so this is simply RAY minus 500 minus 250 gives us minus 750 plus REY, and that's equal to 0. So let's simply say minus 750 over to this side of the equation. Therefore, RAY plus REY is simply equal to 750. Call this equation 1. So we have two unknowns in one equation, which makes it impossible to solve. So we simply take moments. And I will always say, take moment about the point where we have numerous of forces. So we simply take moment about point A to reduce the effect of these two forces at that point. Okay. Take moment at point A. Okay, at A, summation of moments at A is equal to 0. Let's consider anti-clockwise moment to be positive and anti-clockwise moment to be negative. Okay. So if we take the moment of this force about point A, This force is acting downwards, which means it will turn in this direction to point A, which is simply what? Direction of our moment clockwise, so it's positive. And distance it takes this force to get to point A is simply 2.5. So we simply have that force 500 multiplied by 2.5. Next, we'll have the 250 kilonewtons force also acting downwards. That means this force will also turn about this direction to point A. It is still clockwise, and total distance it takes this force to get to point A is simply 3.3, as can be seen here. So you simply have plus 250 times 3.3. Finally, we take the moment of this force REY about point A. Okay, so distance it takes this force REY to get to point A is simply 2.5 plus 2.5, which is 5 meters. Therefore, and again, this force is turning upwards, anti-clockwise. It goes in this direction to point A, which is anti-clockwise, so it's negative. We simply have minus REY times 5. The whole of this is equal to 0. So we expand now. 500 by 2.5. We have 1250 plus 250 multiplies 3.3. We have 825 minus 5 REY, and this is equal to 0. So we evaluate 1250 plus 825. We have 2075, and that's minus 5 REY, and that's equal to 0. So we simply say minus 5 REY over here. Negative sign cross and equal sign becomes positive. We simply have 275 is equal to 5 REY. So we make REY subject by dividing through by 5. Therefore, REY is now 275 divided by 5. Please give me this value. It's simply 415 kilonewtons. So REY is 415 kilonewtons. What? RBY, sorry. Please, sorry, this is RBY. My God. Okay, so this is RBY, because this is point B. That's RBY. Okay, so we have RBY to be that. RBY. RBY. Okay. So we have RBY to be 415 kilonewtons. Now, to find RAY, we simply substitute that into equation 1. So substitute into equation 1. From equation 1, we have RAY, simply RAY plus RBY, and RBY give us 415, and that's equal to 750. So you pick it out, 750. So to make RAY subject, we simply send 415 over here. So you simply have 750 minus, of course, positive sign cross and equal sign becomes negative, becomes minus 415, and therefore RAY is equal to, you have 335 kilonewtons. So this becomes the reactions at point A and point B. Now, having known these reactions, all we need to do is simply you put back the reactions into the original beam. Since you have UVL and UDL, put it back into the original beam, then we can now start the shear force and bending moment analysis. It's a very simple thing. Okay, let's try it and see. So the original beam is simply this. We have here to be 100 kilonewton meter, and we have here to be 200 kilonewton meter. Okay, we can split this. Okay, this remain 100 kilonewton meter per meter, and this also remains 100 kilonewtons per meter. We know the reaction at point A now. We know the reaction at point B as well. Please call me these reactions. What's RA again? 335. So RAY is 335 kilonewtons, and RBY is 415 kilonewtons. Having known these reactions now, we can now start our shear force analysis. Remember, distance apart is 5 meters. Okay. All right. So shear force analysis. Okay. So I said shear force simply means the stepwise summation of the entire force acting on the beam from beginning of the beam at each point of the beam to the end of the beam. Okay. So considering upward force to have positive shear force and downward force to have negative shear force. So the force that exists at point A is simply RAY. Therefore, shear force at A is simply 335 kilonewtons because this force is pointing upward, so it has a positive shear force. Now, we are supposed to take shear force at point B, but notice that this is actually a double loading of both uniformly varying load and uniformly distributed load. Because of this UVL and UDL, all we need to do is, first of all, we take a section. You consider a section XX at a distance of x from point A. So distance from point A to the point of section remains x meters. Okay, remain x meters. Okay, distance from point A to the point of section is simply x meters. Okay, now if distance from A to the point of section is x meters, what then is the point load about the point of section? So we simply find mod shear force at the point of section, shear force Xs, and that's simply equal to, not forgetting, this 335 kilonewtons force move from point A and encounter this shear force, this section point. So also bring it down. You have 335 kilonewtons force. This force moved and encountered the UVL and the UDL along the point of section. Now, due to this section, remember we have a UVL and a UDL on top of one another. We want to find the shear force of these values about the point of section. First of all, we consider that of the UDL first, the uniformly distributed load. The length covered now is x. From point A to the point of section is simply x. To convert a UDL to a point load, what do? Simply multiply that UDL load by what? The length covered. And the UDL load is simply 100. So 100 times length covered now is x. It becomes minus 100x. Minus because UDL load is always pointing downwards. Next, we consider the UVL, uniformly varying load. To convert the UVL to a point load, we simply will take the area of the shape. Area simply becomes, again, it's still going to be minus because the load is also acting downwards. It becomes half base. Base is now the length covered by the UVL, and this length in this case is now what? X. So half base x times height. Height is the maximum load of the UVL, which remains 100 times 100. So this becomes shear force about the point of section, or shear force, simply shear force AB along A to B. You can simply call that shear force AB, which is shear force along A to B. So you simply have here 335 minus 100x minus, of course, 1 over 2 times 100 will give us 50x. So at point B, x becomes total length of the UVL, which is simply 5 meters. At B, x extends from point A down to point B, which becomes the length of the UVL, as can be seen here. Length of UVL is simply 5 meters. Okay. All right. So at B, x is simply equal to 5. Therefore, wherever you see x, put the value as what? 5. The shear force becomes shear force at B, and this is equal to okay, so please take note that at point B we already have an upward force there. At point B we have an upward force, so because of that we simply call this shear force B prime, which means initially at point B the shear force becomes 335 minus 100x. 335 minus 100, in place of x, x now is 5, so it becomes times 5 minus 50x. Okay, in place of x, x is also 5. We have this. So shear force B prime is now equal to 335 minus 100 times 5 gives us 500 minus 50 times 5 gives us 250. So do this for me. Shear force B prime is now equal to 335 minus 500 minus 250. minus 415 kilonewtons. But at point B, we have an upward force of 415 kilonewtons. Therefore, we simply say shear force B prime prime, which means finally at point B, this same force minus 415 encountered an upward force of plus 415, which gives us simply 0. So the shear force analysis always, at the end of every shear force analysis, you must always obtain 0 as the answer. Next, we move into bending moment analysis. Okay, from the law of equilibrium, the moment of every force at every point is always 0. So the moment of this force at point A, since there is no force behind point A, moment at point A directly becomes 0. So we'll put that down. Moment at A is equal to 0. Now, just like we did in the previous case, along A to B, consider a section XX at a distance x from A along A to B. So we are taking a section from A to B. We call that distance x from A to the point of section because of this different kind of loading that we encountered now, UVL and UDL. So we simply take a section x from A along AB. Okay, and we call that distance to be what? X. So we find the moment of these forces now. First, we have the moment of the 335 kilonewtons force about the point of section. Moment is force times distance. This force at point A can take moment about that point, and distance it takes this force to get to that point is simply x. So the moment of that force, this becomes moment along AB. Moment along AB is now equal to, we have 335 times distance it takes to get to the point of section, which is simply x. Minus because downward force will always have negative moment, and UDL and UVL always have a downward force. So the first thing, we convert the UDL first to a point load before we take moment. Converting the UDL to a point load, remember, it is simply multiplying the UDL load 100 by distance cover, which is simply x. Now, after multiplying by x, next thing to do is to what? Place this load at the middle of the length. Okay, place the load at the middle of the length, and if the length now is x, middle of the length simply becomes x all over 2. So times x all over 2, we have this. So this becomes the moment. Okay, so it's just like I've converted a UDL to a point load. Let me explain that over here. Okay, so I have a beam which carries this UDL about this point of section. Okay, this is the UDL now, and distance to the point of section is simply x. And I want to convert this UDL to a point load. I simply say the load is 100 kilonewtons. Okay, kilonewtons per meter. That's the load. So to convert this, we simply multiply 100 by the length covered x. If you multiply 100 by x, you simply have 100x, and you place this load simply. This is the point of section, not forgetting x. And we want to take moment of this UDL about the point of section. So you simply have this. Place this load now at the middle, okay, which is now 100x. The middle now is simply what? X all over 2, and here is also x all over 2. Remember, this is the point of section xx. So you want to take moment of this 100x load about the point of section. It becomes 100x times total distance you take this load to get to the point of section, which is simply x all over 2. That's actually what happened there. Okay, so after converting to a point load, we have to place it at the middle. That's x all over 2. That's for the UDL. Now, for the uniformly varying load, to convert a UVL to a point load, remember, you take the area of the shape, which is half base times height. Okay, so we indicate that minus half base. Base is now the length covered, which is x, times height is the maximum load of UVL, which is still 100. The maximum load of the uniformly varying load is still 100 kilonewtons per meter. Okay, this is now the point load, but then we need to take moment about the point of section. Okay, so now we want to find the moment of the uniformly varying load. Okay, so remember, let's now do a little analysis here. This is my UVL, okay, about the point of section XX, okay, and the distance to the point of section, we'll call that x. The maximum load of the UVL remain 100 kilonewtons per meter. So first of all, to convert this UVL to a point load, we simply take the area of the shape, which is simply half base. Base now is the length of the UVL about the point of section, which is x. So x times height. Height is the maximum load, which is 100. So this will simply give us 50x. This becomes the point load of the UVL. Now remember, you now place this at 2 over 3 of the length from the tip. So this is the tip, x is here as a length, so 2 over 3 of x is from the tip, then from the base is 1 over 3 of x. So which means you have this point going to be somewhere around here. Distance from the tip to this point is 2/3 of the length, 2 all over 3x. That means from here to the point of section, remember here is the point of section, xx remains 1 all over 3 of x. And if you add these two together, you're of course going to get x as the answer. So which means the moment of this load, remember this load now is 50x. The moment of this loop becomes 50 times distance it takes to get to the point of section xx, which is 1 over 3 of x. So that simply means you add that here, minus 50x times 1 all over 3 of x. So it becomes the moment equation for the UVL. Okay. So if you want to rewrite this, I can take this off now. Okay. So moments along AB is now equal to 335x minus, this gives us, okay, take note, 10x times x over 2 becomes 50x squared. And here we have 50x times 1 over 3x, which is approximately 50 over 3 times x, which is 50 over 3x squared. What's 50 over 3? Eh? Okay, so 50 over 3 gives us 16.67 minus 16.67 times x squared. Okay, so of course we have x squared here, we have x squared here. If you want to see evaluate that, you can further evaluate. Moment AB is simply 335x minus 150x squared, we have 16.67x squared. This can simply give us 66.67x squared. So of course we can approximate 66.67 to be 67. So it means moment AB equals 335x minus, approximating this, it becomes 67x squared. Now at B, x is simply equal to what? 5, which is the entire length of the beam from A to B. X becomes 5 meters. Wherever you see x, put in the value as 5. So it becomes moment at B equals, this becomes 335 into x. X is now 5 minus 67 into x squared, which is now 5 all squared. This is equal to 335 times 5, give us 1675 minus, this becomes 67 times 25. 5 squared is 25. So you have there to be 1675 minus 67 times 25 also give us 1675. Therefore, moment at B is simply equal to 0. At the end of every moment equation, you must always have 0. At the end of every moment analysis, sorry. Okay, so having done with this, next is to now plot the diagram. So let's plot the diagram now. Okay, so we know reaction at A. This is 335 kilonewtons. We know the reaction at B. This is 415 kilonewtons. Okay. All right. So we simply plot the diagram now. Trace point A and point B down. You trace point A down. You trace point B down. So we start with the shear force. Shear force at A give us 335. Let's pick the highest from the lowest. And shear force at B is 0. So you simply put down your origin line. Shear force at A is simply 335. You have here 335 kilonewtons. Trace out this point. So this is your origin line, which is 0 mark.